what we discussed last time. So, okay, please maybe write me in chat whether you can hear me, because I never know, of course. Can you hear me? Okay, perfect. Okay, so let's start with the repetition. So we discussed last time the derivatives, right? So we discussed the derivatives, and then we discussed how to take them and different rules. So those were the basic rules. Those was a very, so this is, for example, for the power function for a polynomial, and so on. So I think we discussed many things. So we discussed different. So we discussed like sum, difference, multiplication. Okay, yeah. Multiplication. And other things. So also, so logarithmic, exponential, and trigonometric functions, right? So that was last time. So let's now, so we didn't do much in the way of examples, but let's now do some computations. So today we will try to do, I will just use Paint as the way to write things. And of course, this is a little bit slow, but okay, maybe it's not so bad. So let's start with this limit. So let's start with 2. So you have this limit, which I'm not going to rewrite because, well, it's right. So we have sine. Oh, let me delete it. So we have so this limit, how to compute it? It's going to be limit alpha goes to 0, and then I write here sine alpha divide by 12 alpha. So I just write here the same thing. So remember, this is our limit here. And times so I first try it, and then we see what exactly is going on. Divide by sine of 5 alpha. So, and this limit equals to. So imagine that I started with this limit, which I do not write. Not to write everything because it's too time consuming. And then we still have 12 alpha and divide by 5 alpha. Right? So I just multiplied by 5 alpha or 12 alpha and divided by it. So no change is made to the expression. But you see why this is made. Now you remember that for example, here you have the something indeterminate. Well, I think they're called magical limits. So you remember, so let me just go to the textbook because that was surely where it disappears. Yes. So this is one of the limits. This is the limit that is very important. Sine theta divided by theta equals to 1. The limit goes to 0, goes to 1. So when theta goes to 0, this is more, you can replace by 1. And so alpha goes to 0. So 12 alpha also goes to 0, right? And therefore, this goes to 1, this fraction. And the same for this fraction. This also goes to 1 because 5 alpha goes to 0. And here, of course, we can cancel alpha. So, and what we are left with is going to be just 12 over 5. And this is going to be the answer. Right? So I hope this is clear. Okay, the next thing. Now let's also do the derivatives. So let's immediately do the composite functions or the chain rule. So we need to apply the chain rule here. So, for example, the first one. Okay. Oh, so if you have any questions, you can ask about this limit. But yeah, I hope it should be fine. Okay, then I remove it. Yes, so please write in chat your student ID number. Okay, as to mark your presence. The chat is saved automatically. Okay, so we consider this function here. So we take the derivative. So okay, let's first write f of x equals to g of h of x, where g of x, well, I can actually use a different variable. Let's say g of z equals to z to the 4th, and h of x equals to 6x squared plus 7x. Right, so you see what is going on here. So this 4 is a little bit okay. Doesn't matter. Okay, so yeah, okay, maybe better to use x because it really doesn't look nice. So let me just use x. Okay, so f is the composition of two functions, and So you see what is going on. We first apply the inner function a in this case. So it gives us this kind of things that yeah. So it gives us this polynomial, and then we take it to the fourth power. This is g. So and then so the derivative of f then is going to be the derivative of g applied to h of x times the derivative of h. Okay, and this is also from x. Okay, so and now we can compute the derivative of f by the normal. So the derivative of g is going to be fourth power. So it's going to be 4 times x to x cube, right? 4 times x cube, and then we apply it to h. So it's going to be 4 times this expression plus 7x, and then it's going to be so it's going to be a cube right here, and then we'll multiply by the derivative of h. So multiplied by, okay, and the derivative of h is this is going to be 12x plus 7. Right, so this is the composite function. So to compute the derivative of the composite function, you need to know the chain rule, which is basically this what is written here. So this is basically the chain rule. Right, and then of course you need to be able to compute the derivatives for elementary for kind of the blocks of the chain, so to say, for the for this g and h, right, for the functions whose composition f is. So in this case, both g and h are polynomials. So this is simple, but they can be trigonometric or exponential or something. So yeah. Okay, so we will now move to the next example. So I'm going to delete this writing if you don't have questions. Okay, then I'm just so it's going to be gone. Okay. So let's consider, for example, this example, right? So here we have a composite function. So example 5, which is okay, I will write it. So let me try this. So it's equals 2 sine of 3x plus tangent of x. Okay, so we have this function. So when computing the derivative, it's not necessary every time to write what are the kind of composite functions, right? so in this case, it's going to be sine the outer function, then the inner function is going to be it's going to be this 3x plus tangent x, right? So we can, I mean, usually you just proceed directly. So the derivative of sine is cosine. So you just write cosine, but you don't write x, but you write of the same thing as below, right? Plus tangent of x. So, and this is already represents the first multiplier. So this is the derivative of the outer function applied to an inner function, right? So sine is the outer function. So this expression in the parentheses is the inner function, and so you take the derivative of the outer function and apply it to the derivative to the inner function. Okay, and then you take the derivative of this thing here right. So and it's going to be 3 plus the derivative of tangent, and the derivative of tangent, I believe, is going to be cosine, right? Cosine square x. Actually, I don't remember the derivative of tangent, but so it's going, of course, it's the easiest way to find is just to consider it as a quotient of sine over cosine. So it's going to be right. So I think it should be this indeed, right? I think this is correct. Yeah, and then this is going to be your derivative, right? So you take the derivative of the first part. Okay, good. So you take the derivative of the first part and then of the second part, and this is what you get. Okay, so I think it's more or less, it's clear, right, what is going on. So and by this thing, using this method, you can find the derivative of a really arbitrary function if you apply it sufficiently many times. Okay, so for example, we have this 24. Okay, or even I want it to be okay. So, but let's say even 24. So there is no new significant challenges arise here. The outer function is going to be polynomial. Okay, maybe let's do 24 just for the sake of illustration. So, do you have some questions about this thing? I think it should be okay. Right? Okay, then I'm removing. Right. So second, I think is the trigonometric reverse. It's 1 over sine, right? So it's either 1 over sine. So it's 1 over cosine, right? So I think it's sectant. I'm not, but this is a reverse trigonometric function. So this is, I can even check. I don't. Yeah, so sec is 1 over cosine, right? So, okay. Good. Okay, so then we proceed to this example. 24, right? So, okay, so I will immediately write the derivative, right? Okay, f prime equals to. So the first outer function you see is the cube, right? So it's going to be, I write immediately, the derivative of cube is 3x squared. So, and then instead of x, of course, I write this thing, which is in the parentheses. So it's going to be e to the power minus 6t plus sine of 2 minus t, and this is squared, times times looks like x, but it's not x, it's times. Okay, times the derivative of this inner function. Now, the inner function itself can be seen as a composite function, right? So somehow you have 3 layers of composition, but this is no problem. So once again, we forget about this. So we only consider this inner function, this one, right? And we forget about 3 and about the square, we forget here. Okay, so the inner function, so this is going to be the derivative of this is of the first summand. Summand is going to be, well, is the derivative of the exponent, right? So it's going to be minus 6 to itself, plus. Now, sine you can itself interpret as a composite function. So this is itself is a composite function, sine of this thing, and this is a separate function. So the derivative of sine is cosine. Is cosine. So you rewrite just cosine of the same argument times the derivative of the argument, right? So the derivative of minus 2t is minus 1. So it's just times minus 1. So of course I could have just put minus, but let's say okay. So, and then these are our outer parentheses, right? So those are okay, and this is what you get. So and then of course we can rewrite it. Well, okay, I'm not going to rewrite it because basically you can see. So this remains the same, right? This part, the first part, then multiplied by, and then you have this parenthesis. Basically, you have here minus. You also then have here minus, and you just rewrite in a nicer way. But so the idea is that in this example we had in fact something like 3 functions. So we had the most outermost function was 3 was x cube. Then here we had a sum, and then here we also had sine of also not of t but of 2 minus t, which is also a function, right? And if, for example, we have here t cube, or let's say t square, right? So it's also possible. What we would get here? So what would change is this part here would change. So we would get cosine of t squared, and then times the derivative of t squared, which is going to be 2t, right? So you see that it's a nested kind of so you have a nest somehow functions, and like you can have generally arbitrary many iterations, function for function or function and so on. But if you compute the derivative, it's still pretty. You just compute it and it's okay. So no significant difficulties here should arise. Okay, so do you have some questions regarding this example? So that was 24, right? That was 24.
Yes. So what happened to 3 at the beginning, before the parentheses?
Yeah, 3 appears. So there is no 3 here, right, in the function.
Oh yeah.
So 3 appears from the derivative of x cubed, right? So it's a multiplier which remains, right? So if we go back to our formula, okay, let me go back here. I think So this is a formula, right? So in this example, this f small was x cubed. So 3 appears just, so if you take the derivative of f cubed, it's x,
Yeah, okay, yeah.
right? Okay, and then it's 3 appears there. Okay. Okay. So do you have some other questions? Okay, good. Right. So those were the examples with composite functions. So once again, there are many more examples. We right. So okay. So let's also do 32, right? For the okay. So what is this? So to determine where in the interval minus 120, this function is increasing and decreasing. So where it's increasing, where it's decreasing. Now, we will talk a little bit more about this also today, but we know that the function is increasing when the derivative is increasing, right? So we start by finding the derivative. So this is the first step. So f prime equals to, so logarithm, natural logarithm. So the derivative of natural logarithm is 1 over x, right? So it's, and then it's going to be, here we have, instead of x, we have this polynomial plus 20x cubed plus 100. And in the numerator, we have then the derivative of, so, right? It didn't, okay, so it should be 1, right? So imagine, okay, I write here 1 times the derivative of this thing, right? But so of course I can immediately write it into the numerator. So I write immediately here, it's going to be 4x cubed plus 60 x squared, and that's it. And so the derivative of 0 is 0, right? Okay. So, and now this is my derivative, and I want to find when it's larger than 0, and or when it's so when it's greater than 0, when it's smaller than 0. Okay, so when it is greater than 0. So we have here a fraction, right? But to solve this inequality, when it's greater or less than 0, so it doesn't matter whether you divide or multiply by a number, well, unless it's 0, of course. So this is something we have to keep track on. But for the purposes of solving the strict inequality, it doesn't matter whether you divide or multiply, right? So there are 3 possibilities. This denominator is positive. Okay, then it doesn't change the sign of the numerator. Second is that it's negative, then it changes the sign. And the third that it's 0. And then the quotient doesn't exist, but the product is then also 0. So somehow you don't change the solution. So this inequality is then equivalent to this inequality. Okay, and then I will immediately write the numerator in this form, right? So I somehow put, so this is 4. So I put x squared outside, right? And then I just also multiply by the denominator, x fourth okay, and this should be larger than 0, right? Okay. So let's have a look. So we should find all the roots of this polynomial on this interval. So our interval is -120. Okay, so here once again we can divide by 4, so it's going to be x plus 15. X squared. And then, okay, this I will just say it's the same, right? Not to rewrite it. Not to rewrite it. Okay, so now x squared is always non-negative, but we can remove x squared, but we must remember that x not equals to 0, right? Because if x equals to 0, then this is 0, right? So and we're looking here for strict, let's say. Then this part is always positive on this interval, right? So whether x minus from -1 to 20, this is always positive. So this we can this doesn't affect the sign. So let's say that okay, we removed x squared, remembering this one. Then we remove this one because it's always positive. Let's have a look at this one. So x fourth is always non-negative, right? And then this is larger than -20. So here we have x fourth plus 20. Okay, so let me here also write this question mark. So this we're solving, right? We're not sure when it holds. So this is larger. So this I remove now x fourth because it's non-negative. And then this takes the minimum value when it's -1, right? The minimal value of the interval. So it's larger or equal that -20 plus 100. And this is, of course, larger or equal than 80. Right? So this is always positive because it's larger than 80 on our interval. So we have just one point. We exclude one point, but on the rest of the interval, the derivative is positive. So the function is increasing then, right, on the entire interval. Right. So the derivative is positive everywhere except 0. But the function is increased on the entire interval because so when you're talking about increasing and decreasing, you actually you want to include those points. So you want to take the closure, right? So then, okay, so we have this interval. So this is 20. This is -1. And then here we have this 0. So let me do it like this. this? Oh, no. Right. So this is somehow not included point here. So everywhere on the interval, the function is positive except for one point. Here is positive. But of course, the increasing intervals also include those points. So the function is increasing everywhere on the interval. Right? Okay. So that was, so here we also needed to find the derivative. And yeah, I hope this is also okay. All right. So, and then, okay, so this is where we finished last time, I think. By the way, yeah, but this is also for the chain rule, right? So you have, I think, composition of three functions. You have square root, then you have the sum, and this is also, this parenthesis cube is also a composite function. So, okay, so this is a standard kind of thing, right? That you just, such kind of expression, you can compute the derivatives, and yeah, it's, you just so it's relatively simple because you just, so it's clear what rules to apply. So we'll also consider integration in this course, and the integration is more tricky because there is always multiple ways you can kind of take, and then you do not see immediately what rule should you apply. So you can try one thing and then maybe it doesn't work out, and then you succeed maybe with a third idea or something like this. But for differentiation, so the rules are pretty straightforward. So it would be much easier to write a program which would do which would take derivatives than it is to write a program which would take integrals. Okay, so this is what basically what we discussed last time, and now we'll also do a little bit of exercises. By the way, today I think we will finish shortly past 6. Okay, so let us now discuss implicit differentiation. So here, so before that, we discussed taking the derivative of a function which is represented explicitly in such a form. Now, this is not always the case. That you can represent your function in like with y on the left-hand side and some expression on the right-hand side. Now we will see now in a moment where it doesn't occur. So if you have this equation, of course you can, and then so the question is to find the derivative. Of course, the easiest way is to just write it like this, which is a legitimate way to write the expression for y. And then you kind of just take the derivative, right? And this is just x minus 1, right? So you use a formula for the power for the polynomial, derivative for the polynomial. So in this case, this is totally sufficient. But now, just for the didactic purposes, let's consider. Imagine that we cannot do this. We cannot do this. And we will see in a moment examples where we really cannot do this. But so here we can write this as a product of two functions, right? So xy equals to 1. Imagine, so x is a function of x, right? So it's an identical function. and y is, okay, function of x. Now you take the derivative as a product. You can take the derivative as a product, right? X, y, so it's a product of two functions, x and y, and then you take the derivative. So the derivative of x is 1 times y plus the derivative of y times x, right? Now they also equals to 1, and the derivative of 1 is 0. So okay, so you start from here, you take the derivative of both parts, right? So if two functions are equal, their derivatives also equals to each other, right? So you have this, and then you compute further. You have this. Here, of course, the derivative of 1 is 0. So this is what you get. Right. So okay, this is just another sign for the derivative. D over dx is another sign. And you remember we wrote, so we discussed df over dx, right? That was a derivative. But also it's conventional to write it also like this. So this is somehow goes into the numerator, right? But because it's kind of too large, people don't write it in the numerator, but write it like this. So this is more for aesthetic purposes. So this is just the derivative of y. This expression I cannot. Mm, okay, never mind. So this is the derivative of y. Right? Okay, and then I delete this. Okay, so this is what you get, right? Y plus x y prime is 0. And this also gives you the derivative of y implicitly as a function of x, because y is also a function of x. Now, of course, in this sense, we can also solve it. And then, of course, if you substitute y for 1 over x, it also gives you the same answer. But sometimes you cannot solve this equation. So if y has some different, if the initial relation between x and y is more complicated than this, so this is the initial relation, then of course sometimes you cannot solve it, and this is how you leave it. So let us consider another example. Right, so this is, let's consider this example. So once again, here we can still solve it. But we see that the function y is not defined uniquely from this equation, right? Because here it's plus minus. But we still can find the implicit derivative here, or we still can find the derivative. This is what we do once again. We take the derivative of both sides. So we have this equation. We take the derivative of both sides. So on the right-hand side, we have a constant. So the derivative of a constant is going to be a constant again. And here on the left-hand side, we have x plus y squared. So we take the derivative, and this is what we get. So we get the derivative of x squared is going to be, okay, even better here, 2x. The derivative of y squared, right? So this is a composite function. So it's going to be 2y times y prime, right? So so you have y square, right? So imagine that f equals to, so f of x equals to y of x square. So this is a composite function, so f prime equals to 2y, which is the derivative of outer function applied to the inner function, right? Because the inner function is y, and then the outer function is, let's say, z square, z square. The outer function is of z square, let's say. And then, so it's going to be 2y times y prime, right? So this is by chain rule. This is the chain rule. So this is what we used here to find this expression. And then on the right-hand side, we have 0, because here we had 9, and the derivative of 9 is 0. And this is then what you get, right? And this is okay. So this is, now here, you of course, you can replace y with one of those, but you see it's not uniquely defined. But in fact, this is true. This is kind of true for every point of this thing, because of course we can plot this function y, right? So the plot is going to be, so we have the coordinate system, and then we just, so the plot is going to be in fact a circle, right? So with here it's going to be 3, right? So the radius of a circle is 3. So the plot is going to be circle, and then of course you see that if we take an x, right? So if we take an x, for example, here, then y is not uniquely defined, because there are two values of y which satisfy the equation, because this line intersects the circle in 2 points. But this equality holds in both of those. Okay, so this is how you can find the implicit derivative. You just take the equation that you get and take the derivative for both sides, and then try to solve it with respect to y prime, right? And note that y here involved on the right-hand side. Okay. And so here we have already indeed even more complex examples. Now, if you have such an example, in the previous example, you still could solve the relation to determine y explicitly, right? So that was our previous example. And we could still kind of solve explicitly for y, right? So it's okay. But in this equation, we just cannot do it in elementary functions. So it's just not possible, period. So what's the only way to do, the only way to proceed here to find the derivative is to use this technique that we just discussed. So we take the derivative of both parts of the equation. Now here we have x cubed y to 5. So this is the derivative of the product, those first two summands. 3x squared, which is the derivative of x cubed, times y to 5, plus, now the derivative of y to 5 is going to be y to 4 times y prime, right? Once again, this is y is itself a function, and yeah. And okay, so 5 goes in front, and then x cubed remains, right? Then you have plus 3x here, so you have plus 3 here as well. here you have y cube plus 1, so plus 1 goes away in the derivative, and then we have 3 times y squared times y prime. Right, so I hope this is clear. And now we try to solve it with respect to the derivative. And then, yeah, so imagine that once again, x and y are treated as somehow as quote unquote known, but y prime is your unknown. And so you solve with respect to y primes, and this is what you get. So you get this expression. Okay, and that's it. This is the answer. This is the derivative. And this is also true here. So, okay, and let's consider also this, for example. So this, because we didn't discuss explicitly the derivative of sec, and this is we don't consider now, but of course you can also check it. So it's the same principle, but let's say here. Right, so take the derivative of both sides. So the derivative of the exponent is exponent itself times the derivative of this expression in the exponent, right? And taking the derivative of, so the derivative of 2x is 2, and then 3y is 3y prime, right? So this is the derivative of the left-hand side. Now we have the derivative of the right-hand side. Here we have x squared, okay, so 2x, right? This is the derivative. And then we have the logarithm. And once again, we take the derivative of the logarithm as of a composite function using the chain rule. So remember, the derivative of x is the derivative of, say, of logarithm of x is 1 over x, right? 1 over x. So you take this expression and put it into the denominator. In the numerator, you take the derivative of this expression. So x times y cubed. So this is the product. So the derivative of x is 1. So this is y cubed times 1 plus 3 y square y prime times x, right? So in the numerator here is the derivative of the denominator. Okay, so this is what you get. And now you have to solve with respect to y prime. So this requires some computations, right? So you have to open the parentheses and then write it like this. Okay, and then they simplify here, and then they put everything with y prime to one side, and this is what they come up with. So this is the derivative for the implicit function, right? So an implicit function is given by an equation, for example, by this one. It may not be uniquely defined, but you can still always, well, not always, but in our cases, in this course, you can take the derivative and find y prime. Now, and by the way, you can also compute it, like, for example, if you have a point, like, for example, you have a point like 1, 2, x equals 1, y equals to 2. First of all, of course, you have to check that this point satisfies this equation, which it probably doesn't. Right? So, but assume that we have a point which does. Now, so let's say of course, we can find such a point if we spend some time, but this is, let's say, not very interesting. So let's say we have a point x equals to something and y equals to something. then you can just find y prime by plugging x equals to something. So x, let's say, equals to a, y equals to b, where a and b are numbers, right? So just let's say 1 and 2 or something like this. And then you plug in here y prime uh, equals to, and then you plug in a instead of x and b instead of y, and you can find your value for y prime. Okay, so let's make a pause here, right? So let's make a pause. I say maybe 10 minutes or something like this. Maybe let's say 8 minutes. Okay.
Okay.
So maybe if you have some questions, you can think of yeah of the questions meanwhile. Okay, so I'm going to go off for a while, and I will come back in 8 minutes or so. continue. So that was our last example, and we're talking about the explicit differentiation. So now it may also be the case that both functions, both variables are function of the third variable. Okay, it's common notation to denote this third variable as t. So x is a function of t and y is a function of t. Now we can now consider them taking derivatives with respect to t. So for example, we take an equation and then we can differentiate with respect to t. Now, okay, there is nothing else you can do, but note that, of course, if t is just x, so you consider that t equals to x, then this is going to be 1, x prime is going to be 1, and you will end up with exactly the same situation as if you just consider y as a function of x. Okay, so this we're going to skip. Okay, then there are the higher order derivatives. So now the second derivative, the derivative of the second order is just the derivative of the derivative, right? So the derivative is a function itself, right? So this is our function f. This is the derivative. But now you can also take the derivative of the derivative. So this is going to be the derivative of the second order. And then it continues until infinity, if you can do the differentiation. So this is the derivative of the third order. It's going to be the derivative of the second order, right? The derivative of the third order equals to taking the derivative of the second order derivative, and so on. Okay, so there is not so much new here. So for example, if you have this function, you can compute, of course, derivatives of arbitrary order. So for example, here the first 4. Yeah, and okay, so derivative of et is itself, and then you just differentiate the polynomial each time. And please also note here the notation. Now, usually the derivatives, so this is the first derivative, second, third, but starting from fourth, you don't usually make 4 primes, like 4 dashes up in upper script, like super in superscript. But you just write here a number in the parentheses. So if it's 5, you write, is it fifth derivative? You write 5. Okay, so and this is for cosine, and then this is for okay, and this is for this is for this function, right? Also, just take the derivative. So of course here you need to work with the chain rule a little bit, right? But okay, so nothing here in particular, and so on. So basically, higher order derivatives is pretty much the same. But let's now have a look at the implicit functions. Now, if you have explicit function, you just take derivative of the derivative and so on. So it's more or less straightforward. Now, for the implicit function, it is not as straightforward. Let's have this as our relation between x and y. So we take the first derivative, which we have already discussed. and this is what you get. And now to take the second derivative, so you find y prime explicitly, and now you take the derivatives of both parts here, right? And then you take the second derivative, and this is what you get here in the end. So you just take the first derivative, find the first derivative explicitly, and then you differentiate, right? And note that when you differentiate, you also get here y prime, right? Because you take the derivative also here, y appears. So when you apply the chain rule, also y prime inevitably appears somewhere. But then you just deal with it by plugging it instead of y prime. You once again plug in this thing here, which you have found earlier. So you have here still y prime. Okay, so this here they just leave y prime. But of course, you can also just, instead of y prime, you can plug in this thing here, right? And so you will express second derivative in terms of x and y. And then you can continue. You can continue this process, and you can also find the derivative for all the explicit, function, all the derivatives. Once again, in terms of x and y, not only as functions of x, but as an expression of x and y, right? Because this is y prime comes here as an expression of x and y. Okay, so right, and then of course, okay, so there is some functions that it's convenient to take the logarithm first, and then you take the derivative. But yeah, this is so. For example, if you have this expression x to the power x, right? So this is well defined for positive x. What you do is you take the logarithm. So you write it as a logarithm. So this y equals to x to x to x. So you write it as a logarithm, and then you take you differentiate both parts, and this is what you get, right? So much simpler. And then from here you can easily compute it. So this is just a neat trick to compute some derivatives of this form, because otherwise, of course, you cannot apply any direct rules here. You cannot apply neither this rule nor this rule. Okay, and then okay, and this, and now we finish with okay, with yeah. Please write your student number in the chat, better in the general chat. Okay. So now we come to application of the derivative. So mostly, let's say, elementary analysis of the behavior of the function. So what can we say? We can, using the derivatives and some other also things, we can say how the function behaves, where it is increasing, where it is decreasing, and also some other finer things. So, of course, finding the extrema. So in this part, we will also, of course, okay. So once here, I think here mathematically, it's not too complex. It's nothing kind of extraordinary. But this is also, so you also, of course, sorry, for many of you, this is a repeat course, so maybe you will know this. I don't know. But okay, so Okay, change rate we're going to skip. Now, you have the definition of the critical point. Now, if the C is a critical point for this function f, if C belongs to the domain of f, or if f is defined on C, and you have either this or this, if either the derivative is 0 or it doesn't exist. Right, so to find the critical points, we'll talk in a moment why they're interesting, but to find them, you find the derivative, and then you solve the equation, the derivative equals to 0, right? So I think it's clear, right? So okay, so sometimes it's more difficult, but by the way, yeah. So for example, in this example, you have this is the derivative. So the derivative is not defined for t equals to 0. So this 0 is a critical point. Like so we find the derivative, and then 0 is a critical point. And then we assume that this denominator, that the denominator is not 0, and then we find another critical point by looking at the solution to this equation, that this equals to 0, right? So we equate this to 0, and then we find t equals to 1/5, right? So equate the numerator to 0, so t equals to 1/5. So you have two critical points. Now, what do the critical points tell you? The critical points tell you that there are maybe either an extremum, either a maximum or a minimum at this point. Yeah, so there are many examples. Of course, I invite you to look at them after the classes. Okay, so now this is a definition of a maximum and minimum, so of an extremum. So I'm not sure, by the way, where the accent is. Let me see.
Extremum.
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 Okay. So okay. So maximum and minimum is an example. So maxima and minima constitute extrema, right? So an extremum is either a maximum or a minimum. Right. So now you have a global maximum and minimum, or local maximum or minimum. Now the definitions are self-explanatory, right? So I think that global is on the domain, local is, well, around a point locally. So this is an illustration. So this is, for example, both local and global maximum, right? Of course, every global maximum is also a local maximum. But this is a global maximum, and this is a local maximum, right? So this is, you see that it's the largest thing in the neighborhood, but it is not the largest value globally. And the same with minimum. Okay, so of course, one way to identify the extrema is just by plotting. And if you plot x squared and for this function on this interval, it's pretty obvious what is the maximum and the minimum value. But of course, typically to identify the extrema, we have to look at the critical points. Okay, so then the extrema exists. So if you have an extrema at a point C, so it's either a maximum or a minimum, then x as C is going to be a critical point. Now, it means that either the derivative exists and is 0, or that the derivative doesn't exist. So here they formulate a little bit differently, that they formulate that if it exists, then it is 0. But then, of course, it may also just not exist, right? So there are two options. So this is important. That so if you want to find the set of all the local extrema, then you as we will see below, you find the set of critical points and then just check every critical point. Okay, so, and then of course, if you're working on the interval, then you have to check the boundaries of the interval. And this is how you can determine all the extrema on an interval. So all local maxima, so every local maximum, every local minimum, and also find, of course, the global one. Okay, so let us now see how to find the absolute maximum and minimum. Okay, this is, of course, only true for the continuous function. So the function must be continuous on the entire interval. So this is kind of step 0. Let's say, so step 1 is find all the critical points. And then in step 2, you evaluate the function at every critical point and the endpoints of the interval, right? So you evaluate at critical points and the boundaries of the interval. And then among those, you find the absolute maximum, so the maximum and the minimum. So this is, you just take the largest and the smallest. So this is an example. So we have this function on this interval. So we have this function on this interval. So we take the derivative. This is the derivative. We find critical points. So the critical points are the values where the derivative is either does not exist or is 0. So we see that the derivative exists everywhere. The derivative exists everywhere, and then, but the critical points are -2 and 1, right? So, and they of course lie within our interval here. So, and then we evaluate the values of function at every critical point and on the boundaries. So -4, 2, -2 and 1. So -4, 2, -2, 1. So you have those points, and then so you have already found the maximum value on the interval. This is going to be the largest value among those, so it's going to be 24. And the minimum is going to be minus 28. This is going to be the smallest value. So you have found the extrema in this way. Okay, then here's another example. Okay, so once again, it's a polynomial. So you take the derivative. They don't even write it explicitly here. There's the same, it's the same function, right? So this is, yeah, it was the same function, so the derivative is the same, right? So the derivative is the same. So the difference in this case is that, so the zeros of the derivative, so by the way, I'm not sure if we talked about it, but zeros of a function are the values of argument where this function is 0, right? So for example, for the derivative, the zeros are -2 and 1. So it's a little bit, sounds maybe a little bit strange, because you say, well, 1 is 0 for this function, right? So kind of 1 is 0. So, but okay, this is the terminology. So, so it's -2 and 1 for the derivative. Now, -2 lies outside of the boundaries, so we do not consider it. We exclude -2 from our analysis. So we just evaluate on this, on 1, which is the second 0, which lies within this interval, and on the boundaries. Boundaries are 0, 2. And here, once again, we find the maximum, absolute maximum is 8, and the minimum is -3. Okay. Okay, then, so this can be formulated in such a way as a problem. So suppose that this represents a population size of a certain species. So what is the minimum and maximum in the first 4 months? Okay, so we have a function, so we find the derivative. So to solve the equation when it's 0, so we solve this equation. So to find when it's 0, so these are the solutions. Okay, so here they find the solutions. Okay, so we also discussed it, I think. So you take arc cosine of -3, 4. You would take, and then you would, of course, do something with it. But okay, so here they just write the immediately more or less solutions, right? So those values are arc cosine, which they presumably computed on with some library or something. So this is what you get. These are your solutions. Now your interval is 0, 4, right? This is your interval. So you have to check which values here belong to this interval 0, 4. Right, and then they just plug in, right? So now if n is negative, you can see that, so pi over 2 is of course about 1.57, right? So this is going to be a negative number. So n negative we can exclude immediately. And then we just check small values of n, so that the roots are less than 4. And then they check, and they just compute and find, so they find those 5 points, I believe. So this is 1, 2, 3, 4, and 5. And then, so those are the points. And then you also evaluate for those points and the boundaries. And this is what you get. So you evaluate, this is what you get. And then you find the maximum and the minimum here. So the minimum is 100, and the maximum is going to be what? It's going to be this one. This is going to be the maximum, right? And yeah, so this is how you do it. Okay, so then there is one example. There are more examples here. So, yeah, maybe you could also have a look. If you want to kind of, if you feel that you need to have a look further, than you just have a look at further examples. Okay, so do you have some questions about this procedure? Okay, so okay, let's move further. So okay, let's consider this example. So here you have this function. You're also given the interval. So we find the derivative, and this is what we find in the end. So we will compute the derivative. This is what we come to. And now you have two critical points. The derivative is 0. This is one critical point. And another is the derivative does not exist because the denominator is 0. So you have two critical points, and then you have the boundaries of the interval, right? So the boundaries of the interval, those with boundaries. So, right. So let us recap once again. You have a function and an interval. You first start, and you are asked to find the extrema, to find the maxima and the minima, or the absolute maximum and the absolute minimum. So you start by taking the derivative. You start by taking the derivative because you look for critical points, right? So the critical points are your goal now for the moment. And then you compute the derivative, and then you look for two kinds of points. Either the derivative is 0 or it doesn't exist. So in this case, you see that this is a quotient. So the quotient is going to be 0 if numerator is 0. And the quotient does not exist if the denominator is 0. So you look for the points where this is 0, and then also this is 0, right? So you find those points. Once again, here you're interested only in the points that lie within the interval. So this is the interval -5, 1. And the points that you find do lie within this interval, in this interval. And then you evaluate your function at those points. And then you take the absolute minimum and the absolute maximum, right? So it's going to be 0, the maximum, and -15, the minimum. Okay. Okay, so the derivative is very, of course, useful in finding the extrema of a function. Now we move toward the plot. So, of course, it's also knowing the derivative helps a lot in making a plot of a function. So this is the definition of increasing and decreasing function, right? So this is pretty self-explanatory, right? So if you take any two values in an interval, then if second value is greater than the first value, then function the second value is greater than the function at the first at x1, right? So this is and then the decreasing is when the sign is reversed, right? So it's exactly the same definition, just the sign is reversed. Right. So, and so these are theorems. Of course, I think we have also discussed it previously already, also today. But so those are the facts that are very useful in working with plots, in making plots. So if the derivative is positive on an interval, then f is increasing. If the derivative is negative, then f is decreasing. And if it's 0 on an interval, then it's constant on an interval. But this doesn't happen too often, but okay. Okay, so, and those facts can help us evaluate, or rather to plot the function. So we're given this function. We find the derivative. So in here we look for zeros. So we see that x squared we can put outside, right, as a common multiplier, x squared. And then you have this polynomial of second order, which we also can represent in this form, right? So this is what we end up with. Right. So we see that there are three roots of the equation f prime equals to 0. It's also the three roots, and of course there are f prime is defined at every point, right? So therefore those are your critical points, right? So we have three critical points. Now what we do next is illustrated by this picture. So you have those three critical points, -2, 0, and 4. Now, what they do here is, it means, so those are the critical points. It means that the sign for f prime here is the same everywhere, right? So in each of those intervals, the sign is preserved. The sign can only change between intervals. So, and then I think we have also talked about this offline a little bit. We mentioned this offline, right? So to find the sign here, you can just take a single value and compute. So they take here -3, and this is what they compute, and so it's negative. Here they take -1, it's positive, so it's positive. Here they take 1, 45, positive, so the sign is positive everywhere. And then here it's negative everywhere, right? So this is a simple way to kind of to determine the signs, so where the function is positive and negative. So we're here interested in for the derivative, because so we want to find where the derivative is positive and where it's negative, so that we can then use it and find where our function f is increasing and where it is decreasing, right? So here we found those intervals. Okay, here they also warn you against right. So of course, so we have to compute the values of the derivative, not the function, right? So be careful here. But also, I think some people, well, it's also a mistake that it's possible to make. That, for example, you find here negative, right, in the first interval. and then you kind of assume that it alternates. So it's negative here, so it must be positive here, negative here, and positive here. But this is not quite how it works. So the intervals, the signs do not have to alternate between the intervals. So you have to check for every interval separately. Okay, so and then based on this picture, we find that, for example, here it's negative, and here it's also here it's negative, and here it's negative. So here, those are the intervals where the function decreases, and then those are the intervals where it increases. Okay, and let's now attempt to sketch a plot. So what do they do here? So they compute the values at the minimum. So that was the minimum, remember? And this is the maximum. They compute those values. And then they also found that at 0, it was 0. The derivative was 0. And then they plot it in this sense. So, of course, when I think it's better when you plot, it's better to make more values. I mean, it's nice to determine how the function behaves in this sense, or even in this sense. So this is very nice to have. So this you should also have, of course. Then it's also nice if you just compute, for example, some additional points, 1, 2, 3. Why not? I mean, so this is the minimum, and then you know that the derivative here is 0. So this is how. So derivative is 0 means that the line looks horizontally, locally at least. That the curve, I should say, it's not the line, it's the curve, right? The plot is here. So the plot function is the curve. So you have here, it looks almost horizontally at this point. Okay, and then it's increasing and it reaches this point and then it starts to decrease. And here it's also decreasing, right? So because here you have, okay, this is how this is DEC decreasing, and here it's increasing, and here it's decreasing again, right? So, and this is the schematic plot of a function. Okay, and then of course, now we talked a little bit. Okay, so let's maybe have another break, right? So in a few moments, so just before that, so we talked like maybe 20-30 minutes ago about how to find an extrema of a function on an interval, right? So we talked about it some time ago, a few minutes ago. So what we discussed, let's also recap. You find all the critical points of the function, and then you evaluate the value of a function at every critical point and on the boundaries, and that's it. And then then you choose the largest and so the greatest and the smallest values, and that's it. Now you can also a little bit simplified if you look so by using this. So this is what you can also say, but of course this is optional because sometimes you don't need to do it, but those rules hold, and so those rules hold, and yeah, sometimes they can be useful. But it's easier to just, of course, find the critical points and compute typically. But okay, sometimes you can use a finer criteria to determine whether it's maximum or minimum or neither. Okay, so let's have another break, maybe 10 minutes, okay? So if you have some questions, you can think of the questions. And yeah, so I will also go offline for 10 minutes, for about 10 minutes, okay? So. Okay.
Hello.
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 So let's continue. Okay, so let us continue this example. Find all the critical points and classify them, and give the intervals of increasing and decreasing. So we'll start by looking for the derivative. This is the derivative. And the critical points are either, so when this is 0 or don't exist. So these are the critical points. Then it's convenient to draw such a picture. And determine, so the critical points are plus minus 2, so plus minus 2, and plus minus this value, right? So you have 154, 1.549. So we compute how the derivative behaves in those points. So here it's positive, here it's positive, here on this interval it's negative, here it's positive, and here it's again positive. So this is the conclusion, right? So it increases on those intervals and it's decreasing here, right? So here it's plus, here it's plus, here it's minus, here it's plus plus. So here it's increasing, so it's increasing here. Then here it is decreasing, and here it's again increasing. Right. Okay, so let's now think. So the function is well defined everywhere. Oh, sorry, not everywhere. It's all right. It's well defined because it's cubic root, so it's well defined everywhere. So here it's increasing, increasing, increasing up to this point. So this must be a local maxima, right? Then it's decreasing, 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 all the way to this point. So this must be a minimum because it's decreasing to the left and increasing to the right. So this must be a minimum. And then it is increasing. So there should be one local maximum and one local minimum. And this is exactly what's going on here as well. So this is how the function looks like. So you see that, so this is here, the derivative is 0 here and here. And so it's increasing and decreasing, okay? Now here, the derivative is actually doesn't exist because it's divided by 0. So there is 0 in the denominator, which means that near this point, the derivative is very, very large. So the derivative is basically infinity here. So the line is vertical at this point, more or less. It's a vertical. The curve looks like a vertical line locally. Okay, so let's consider another example. Okay, so there is a formulation. But let's say that we immediately look at the simplified formulation when the function is increasing and decreasing on this interval. Okay, so we'll find the derivative, solve when it's 0. Okay, so this, of course, we can find that tangent of something is square root of 3. It should be right, pi over 3, right, plus right, so it should be this is pi over 3 probably, imagine. So okay, so you have two series of solutions, and then this is so pi over 3 plus pi plus 2pn, right? So this is pi over 3 plus 2 pi n, and this is pi over 3 plus pi plus 2 pi n. So you have two series of solutions, and then we check which points of, from those solutions are in this interval, right? So we just compute, take n equals to 0, n equals 1, n equals 2, and so on, and minus 1 also, and c. So you have 4 points of zeros. So this is your interval here. You remember, we're going from minus 25 to 25, right? So these are 4 points in this interval, so designated by dashed lines, right? So here it's negative. We take 1 point and compute, so it's negative. Here, so here it's negative. So sorry, here it's positive. Here it's negative, positive, negative, positive, right? So therefore, and this is the derivative. So therefore, here the function is increasing. Here it is decreasing on this interval, then again increasing, then decreasing, and then increasing, right? So this is written down here. And okay, so okay, and they do not plot it, right? Okay, so let me not plot it, because it would be a little bit difficult. Okay, so then okay, so you have this example. So you have the population. The population size is given by this equation. So determine if the population ever decreases. Okay, so we reformulate this problem purely mathematically, right? In terms of mathematics. And then we'll look for the derivative. So they presumably skip this step. Okay, so that was actually, it was done before, right? Okay, so we'll look here for the derivative. So let's, because it's a minute, so maybe let's do it. So you have, and let's maybe plot it also on this interval, 0, 2. So let's just to see how, yeah, just to have an example how it. So we have this function, and we'll look for the derivative first. So the derivative is going to be p prime equals to 2t logarithm of 3t plus t square divided by 3t, right, times 3. No, wait. Right, yeah. Okay, so this equal, right? So this is the product, t squared times logarithm. So this is the derivative of t squared times this logarithm part, plus this t squared times the derivative of the logarithm. Okay, okay, so and this is 2t logarithm of 3t plus t, right? Just plus simply t. Is it correct? Yeah, it looks correct. Okay, so I wrote here plus t, but of course I have to say that here t is 0. If t is 0, then this doesn't exist. So t not equals to 0 for the derivative, right? Okay, so 0 is a critical point. We have to remember it. Okay, so then we look for the solution to this equation. So p prime equals to 0 is equivalent. Okay, so t we can put take as a common multiplier. Okay, so we know that t is not equal 0. So this equals to 0 is equivalent to this expression in the parentheses being 0, right? So 2 logarithm of 3t equals to -1. So this is equivalent to logarithm of 3t equals to -1/2. Okay. So what's next? So it means that 3t equals to, okay, so and now we take e to the both powers. So e, and here we have both we take both parts of the equation to the power e. So here we log e to log a logarithm of 3t is going to be 3t, and e to the logarithm of e to -1, 2 is going to be, well, e to -1, 2, right? 1/2, I'm sorry. And so t equals to 1/3 e to the power -1/2, right? Okay, so let me see what it is. So I have this is going to be approximately this number. Right? Okay, so I hope it's okay. Okay, so we found a critical point. And so let's now try to make a plot. So what do we do next? Next, we draw this line, right? This is our line. Then this is so I'm just looking. Okay, never mind. How to make a dashed line here? Well, of course, it's possible. Okay, so I'm not exactly sure. So does it matter? So let's say that we have then this line, which is kind of for this value, right? So let's say so let's say here so here we have 0, here we have our value, and here we have 2. So 0, this is the root. So this thing here. So let's say 2, and then here we have 2. Okay, so we compute the derivative. Look here. So here we have to compute something like the derivative of 0, 1. I think. So let's have a look. So this is the derivative, right? This is the derivative. Oops. Now, if t is, for example, 0, 1, then this is positive, right? And then let's look at this. So this is going to be what? This is going to be now the logarithm is increasing, right? And this expression in the parentheses is 0 for this value. And therefore it is less than 0 if we take a little bit like yes. So therefore the derivative is negative here. Okay, negative. And here it will be respectively positive, right? So here we can take t equals to 1, let's say, and this is going to be positive, right? Okay, so the function is decreasing here, and they're increasing on this interval. And so now let's make a plot approximately. Oops. So I'm going to just remove this one. So we're going to make a plot here. So let's have so we have 2 coordinate axes, and then so we have to from so at 0. Now the logarithm of 0 does not exist, but this is another point. So we have this is 0, and this is minus infinity, right? So what is the limit? Now I'm not sure if we discussed it, but in fact this is going to be 0, right? I'm not sure if we discussed it. Okay, so let's say you believe me, and then we'll have a look at it just after we finish the drawing. So the value at 0 is going to be is going to be 0. And then we go a little bit down, right? And then we go up. So this is our, let's say, O2. So here the plot goes down, and then it goes up. right? So we don't know how, but of course, okay, so this is very schematic. Now, of course, to compute the values, to draw better, we need to compute the values, right? So we need to compute what is here and so on. Okay, so we will not do this. Of course, to draw it properly, it's easier to do it in the programming language. Maybe we should talk also about this, by the way, how to do it in the programming language. Right. So let's. Okay. So and now let's return to the limit, right? I said that the limit is 0. So I'm referring to this limit. Limit of t times logarithm t as t goes to 0. Okay, so I think some of you may find it using the L'Hopital's rule. So you just represent it as a fraction, right? I think some of you definitely used it during the classes. So you can write it like this. You can write it like, let's say, logarithm of t divide by 1 over t, right? So as t goes to 0, this goes to infinity, and this goes to infinity. So and then you can take the derivatives and see what's happening. Okay, so if you take the derivative, so which is you can do, right? So you can just take the derivatives of so this is equals, okay, the same, t equals to 0. This is 1 over t, and here is minus 1 over t squared. And this, so this is equals to a minus limit of t, right? This is just t, and this is 0, right? So t goes to 0. Limit of t goes to 0, t is 0, so this is 0. So this is one way to compute it. Right. And then another way, so do you have some questions about it? Okay, so and then another way is to just, well, to make the change of variables. Let's say, so we say that x equals to logarithm of t, and then t equals to e of x. And this equals to limit x times ex. X goes to minus infinity. Now, as t goes to 0, x logarithm of t goes to minus infinity, so x goes to minus infinity. Okay, and this may be, well, first of all, you can, of course, also use this L'Hopital rule here, but well, so the exponential function grows faster, right, than the polynomial. I think we discussed it, right? So you can just think about it also as this. So you can replace x with minus x, and then it's going to be x e to minus x, right? So Or even we can just write it like this. X. Yeah, I think we discussed, right, during the limits that, for example, if you have polynomials, you just divide by the largest. But here we also have that exponential function grows faster than the polynomial, right? So this is 0. Or of course, you can also apply the L'Hopital rule, and then the derivative of this is going to be 1, and the derivative of this is going to be still infinity. So this is going to be 0, right? Okay. Okay, so do you have some questions? Okay, so and let's now all right, so so we have, let's now recap a little bit what we did today. So we started with the implicit differentiation, right? Here we are. So let us come to review. Yeah, so those are the first 3 examples of really implicit differentiation. So you have this equality which gives you y as a function of x implicitly. Implicitly means that y, so it's not like y equals to something of x, right? No, here you cannot write it like this because you cannot solve this equation with respect to y. So, but you can still find the derivative. What you do, you take the derivative of both parts, treating y as a function of x, right? Right, as it was done here, and then you solve this with respect to y, and that was implicit derivative, right? So this is how you find the implicit derivative of y. Okay, so then we discussed the higher order derivatives. So higher order derivatives is just the derivative of the derivative, so there's nothing really nothing new here, I would say. Right, so higher order derivatives is just the derivative of the derivative. So okay, I think this is clear. Nothing to really talk here too much about. Okay, and then we pretty much finished with the derivatives, and then we discussed the following 4 points. We discussed the critical points and what is the definition of a critical point. We discussed the minima and maxima or the extrema and how to find them. So let us recall how to find extrema on an interval. So you find the critical points, and then you you just evaluate, right? So it's not too difficult. Find the critical points, which are the points where the derivative is either 0 or does not exist, and then you evaluate the value of a function at those points. And then, of course, we also at the end we discussed how the derivative looks like. Can determine us. So the behavior of the derivative can determine or can tell us whether the function is increasing or decreasing, right? So let's have this plot. This is a plot. So for example, here I see that the function is decreasing, so the derivative is 0. So if I compute the derivative and see that it is decreasing on this interval, so that that the derivative is negative for this interval, so then the function is decreasing, right? So once again, you have the equivalency. The derivative is negative, function is decreasing. Those are one set of equivalent things. And on the opposite side, you have the derivative is positive if the function is increasing, right? So don't mix up. You have so the derivative is either negative or positive, right? And this determines whether the function is increasing or decreasing, not the other way around. So it doesn't matter whether the derivative is increasing for that purpose, although that matters for something else we will see next time, I guess. Okay, so let's now start to wrap it up. So okay, so let us do as homeworks. So let us do as homeworks. So here number 7. Let's say 4, 7, and 13. And by the way, okay, yeah, I will now send it, right? So I will send it in a moment. So this document, and by the way, I'm not sure that you have it. So let me also. So this document you can find here. So this is the link, right? So this is the link, which I will also send in the. Oops, sorry, I wrote privately. So I have to write it to everyone. Okay, so this is the link with the. So I'm also going to write. Okay, this is also the link that I sent you earlier, right? And so here you have download. And so you have download, and then you have problems only, right? And then this is the file that I have problems only. Okay. And so please practice the implicit differentiation based on those exercises. Okay, then just also that you remember just how to take higher order derivatives. So let's say 2. Right, so just one function you find the derivatives up to 4. So it's not difficult, but just that you remember it. Right. Okay. Okay, here, so this was also discussed today, but very briefly. So logarithmic differentiation, what you do is, so you have g equals to this part, and you want to find the derivative. So you take the logarithm of g, and then you differentiate, right? You remember? So I will write it, and then I will show once again. Right. So for example, this is the classical example. This is a function that you had that we considered, and then we just take the logarithm of this function, take the logarithm, and then differentiate. Right, and then this is what you find. This is what you find. Okay, so it looks good. And then you just solve with respect to the derivative, and then you see here y, and then you replace y with the original function. And so this is just how you can do it, right? So okay, and so and then minimum and maximum. So minimum and maximum. Let's consider minimum and maximum values, because here we just have, so you have to find the critical points, right, to identify minimal and maximum value. So which is section 4.3, right? Right. So here you have a single function which has not too difficult to form, and you are asked to identify all the extrema, right? But on a different intervals. So on different intervals, you can have different answers, of course, but the same function, but different intervals. And then in 5, this is kind of like more conceptual. So you have a function which is defined on this interval. So 5 is just to sketch a plot of function satisfying those properties. So how can it look like? Okay, so you have, of course, a lot of, I mean, there are many such functions. So, but this is just a sketch. So this hopefully should be not too difficult also. Okay, and then I also send this. Okay, so so this is the homework for today. Okay, so please do it. So I think it's of course as you just look at me, how, for example, I look at something, or how when I write something, you don't really do it yourself, and then you can understand everything, and it may seem easy, but then when you start doing it yourself, you may somehow find that you don't remember one step, let's say, or you use just one step that you maybe don't remember, and then it's kind of easy, but then one step you don't remember and you cannot do it. So that's, of course, not the situation you want to find yourself in anywhere. So please just to practice, and so practice makes perfect. Nowhere this is more true than here. So please do those exercises and send them, try to send them to me. If you write them, just maybe make pictures or scan and send them to me or something, right? Okay, so this is the homework. So so this is a homework. So you have all in all, I think, 7 problems, right? Okay, so I hope you find the document, and yeah. So if you have some other questions, you can also ask. And then if not, right, yeah. So yeah, thank you for coming. So it's yeah, so yeah, but by the way, I told in another course, I said that I would lower, of course, the requirements, because of course it's more difficult to study, and of course it's more difficult also for me to teach. So it would be unfair to ask from you what normally would be asked, right? So it should be a little bit, but it should still, it will not be zero, so not like a free passage, but of course, yeah, the requirements for the test, for the passing of the test would be lower than they would normally be, of course. So this is, yeah, I should tell you this. Okay, so thank you for your attention. And then, so if you have some questions, you can still write to me in chat or ask me. But I will now go offline. And then if no questions appears, I will then stop the conference in some 10 minutes or so, okay? Or maybe 5 minutes or 6 minutes. So in a few minutes, I will terminate the meeting. Okay, but provisionally, bye.
Bye. Thank you very much.